my great pleasure to introduce our next keynote speaker. He's a professor in Bolzano, Free University of Bolzano, Italy. If you put his name, Giancarlo Guizzardi, in the Google, the first 16 positions will be his papers, his works, his research works, result of his research work about ontology, foundation of ontology, conceptual modeling, and this domain. So his most known research work is a UFO, so-called UFO, Unified Foundation Ontology. And the another result, it's he's a coordinator of NEMO group. It's a group, Ontology and Conceptual Modeling Group. And this group is responsible for tools for OntOUML. It's very interesting for me because I'm in some way connected with this domain. Today, I will not read the title of his talk, so let me invite you here, and the floor is yours.
Okay. Okay, thank you very much. Thank you very much for being here. It's a pleasure and an honor to deliver this talk. I'm a professor now in the Free University of Bolzano, and I'm still mentoring, coordinating, helping to coordinate this marvelous group in Brazil called the Ontology and Conceptual Modeling Research Group. Thanks for the invitation. This is obviously a work of a lot of people, especially a lot of the work done here was in collaboration with these people at NEMO in Brazil, and also I'd like to thank the extended UFO OntOUML community, in particular the group here of Robert Perglo in Prague, has been doing a lot of really excellent work. So this is a talk about ontologies, right? And the impact of ontologies in information systems engineering. In 2012, so the Millennium Project issues this State of the Future report, which is a 10,000-page book talking about the future and talking about different technologies that will have an impact on the future. And in 2012, this book that makes reference to a number of things like counterterrorism and trips to Mars and different sustainable energy sources and so on, had a whole part dedicated to ontologies and the future of ontologies. So 51 pages dedicated to that. What's even more impressive is that this magazine called the Futurist magazine, which is a magazine read by all policymakers in the world, which makes a 5-page summary of the 10,000-page report, decided to talk about ontologies in that 5-page summary. And in that article, they say, and I quote, "The fast-growing science of ontology could exert a greater impact on humanity than the rise of the internet." This sounds a bit far-fetched, but I would like to defend that it's not. And the reason why it's not has to do with this, with the role of ontologies in semantic interoperability, right? So the importance of the technology is not in the technology itself, obviously, but in the kind of problems it helps to solve. And semantic interoperability is considered the problem of this decade. So this quote from the OMG, in particular in the context of what they are now calling the Semantic Information Model Federation, that gathers proposals to address this problem of semantic interoperability in a larger context. They say that this problem is costing productivity lives and billions of dollars annually, maybe trillions of dollars, and the overall human and financial cost to society from our failure to share and reuse information is many times the cost of systems operation and maintenance. And why is this problem so relevant? Why is semantic interoperability such an enormous problem? I'll start with the semantic part. So an information system is a representation of reality, right? So it's a representation of reality according to a given worldview. The interoperability part is because modern information systems are artifacts that are constructed in a collective and distributed way. So all modern information systems are actually built by putting together information systems which already exist, so by reusing and integrating other information systems, or building systems that will be integrated to other systems, right? So this interoperability problem is inherent to this. The third reason why this is extremely relevant, and maybe this is the main reason, is that most information systems are not just representations of social reality, but they are ways to create social reality. There is this article by Mark Anderson, the founder of Netscape, in the Wall Street Journal not so long ago, in which it's called "The Software is Eating the World," in which he makes this argument that what we have nowadays is basically everything is becoming software, right? So the biggest telecom provider is a software company, the biggest television channel, the biggest entertainment company, the biggest retailer. These are all software companies. Actually, if you think about it, banks are basically IT companies. And the public bureaucracy is basically dealing with this problem of running software. They are basically information process units, right? So it's not only eating the world, but in a very interesting sense, it's creating reality, right? In a sense which is, we used to create reality by grounding certain institutional facts, what the philosopher John Searle calls the connection between institutional facts and brute facts. One example is this, right? So there is some sort of collective agreement that makes painted paper count as money. So that handshake or that painted paper, these brute facts, count as institutional facts, right? And create social reality in this way. Now we are doing the same with software. Because there is a record somewhere that I have, or because there is some sort of distributed state of the blockchain, I have certain money, or I have a certain relationship to someone else. For example, being married to someone else, or being a citizen of a country, or being entitled to a certain property. Now these institutional facts become grounded, not on paper, but on pieces of information, right? And because these information systems are collectively constructed, the facts, the brute facts now, are the facts of this integration, right? So if these facts are wrong, they create wrong, mistaken institutional facts. That's why semantic interoperability is such a massive problem. This problem, semantic interoperability, can be easily defined, and it's really hard to solve. It's basically the problem of maintaining the semantics, the meaning of information, when it leaves the silo in which it was created. So we are putting together a number of information systems that were created in an autonomous concurrent way, and now we are putting this together, but we want to have the semantics, the meaning of this information preserved when it leaves its natural habitat, if you like. Right? So it's about, since given my first premise that information systems are representation of portions of reality, is about finding out how these things are connected. What is the relation between person in the first information system and person in the second information system, or between transplant in the first information system and in the second. And the only way to find that out, what is this relation, if this is a relation of identity or some sort of similarity or specialization or parthood or dependence, what kind of dependence and so on. The only way to find that out is to understand the relation between the reference of these pieces of information in reality. So semantic interoperability is this problem of, essentially a problem of relating different worldviews, that is, different conceptualizations of reality, right? And this problem is unavoidable. The problem is how do we create these conceptualizations of reality? And it's not the case that any conceptualization would do, that we can't carve out reality in many ways, but they are not equally good or suitable. Right? This is nicely explained in this, so there is this article called The Analytical Language of John Wilkins by the brilliant Argentinian writer Jorge Luis Borges, in which there is this, The Celestial Importance of Benevolent Knowledge, a book that offers a certain taxonomy of animals. And the taxonomy you have there is, animals are divided, classified in those that belong to the emperor, those that resemble flies from a distance, embalmed ones, fabulous ones, and so on. Those that just broken a face, and so on. The brilliant psychologist Paul Bloom, in his book How Pleasure Works, writes about this and says, those that resemble flies from a distance is a logically possible way to group objects, but it's not how we naturally make sense of reality. No real language would have a noun for such a category. Real nouns capture something deep. They refer to kinds of things that are thought to share deep properties. As the evolutionary theorist Stephen Jay Gould put it, our classifications don't just exist to avoid chaos. They are theories about the basis of natural order. So in one sense, quoting Plato, what we need to do is to carve reality at its joints, to find the best way or the most natural way to create these conceptualizations. It's not true, however, that there is just one way to carve reality at its joints. And I apologize to my vegetarian friends. So these are all equally valid ways to carve reality at its joints, right? So this idea that there can be multiple equally valid conceptualizations of reality is tightly connected to this problem of semantic interoperability. And this happens even in natural science, right? So there is this article of Science called More Than Words, in which, so it starts with, so there is a quote here by the Stanford medical informatics professor Mark Musin, saying it's getting to be impossible to do work in bioinformatics without knowledge of biomedical ontology. And the reason is, it starts in the first paragraph, most biomedical research labs make up their own private language to describe their particular techniques, material, and measurements. Even medical practitioners have more than 100 ways to describe a simple fact such as the patient's blood glucoses. How can biomedical researchers make the most of the vast amounts of data out there, right? We are here talking about a physical phenomenon, right? Talk about electrophysiology of the heart. The heart obviously doesn't care how we call these things, right? But we have to find ways to describe this brute reality, which are both, in one sense, we should guarantee a intra-worldview consistency within a set of choices that we make to describe reality, but we have to do this in an explicit way such that we can relate these different worldviews in a suitable way. So it's about intra-worldview consistency and inter-worldview interoperability. And this is a problem of ontology for 2,400 years. So in one sense, ontology is about that. It's a calculus of content that offers us a number of tools, number of theories dealing with identity, with parthood, with individuation, with change, with classification, and so on, causality, such that we can do these two things, right? Make a number of consistency operations, choices on how to conceptualize things, and make explicit what we mean by that, such that we can relate to different worldviews. What we have been doing in this area called ontology-driven conceptual modeling is to take this series from ontology, from linguistics, from philosophical logics, from cognitive science, and build tools such that we, computer science, can do this in a safe way. So ontology-driven conceptual modeling is the process or the discipline that tries to take all these theories and build actual engineering tools, language, patterns, anti-patterns, computational support systems, and so on. This talk is also about a particular, let's say, school of thought, if you like, on how to do this. And I refer here to this work that we have been doing for 15 years now on this unified foundation ontology, which is basically one of these theories that tries to provide foundations to many of these classical conceptual modeling constructs, ranging from how to build taxonomic structures, part-whole relations, relations in general, weak entities, attributes, data types, events, multi-level modeling, and so on. And one of the main results of applying this foundation ontology was to build a version of UML, a conceptual modeling language or an ontology modeling language, which is completely based on this foundation ontology, right? And in the following sense, it's a language that all the modeling primitives of the language reflect the ontological distinctions put forth by this foundation ontology, and it's a language whose meta-model incorporates constraints that are based on the axiomatization of the ontology, such that you cannot build models in OntOUML that are not conformant to the axiomatization proposed by this foundation ontology. So this is this language called OntOUML, just to give you an idea of the language, just a gist of what it looks like. Instead of just staying in this very abstract level, in which the only distinction you have is this idea of a class, we make distinction between different types of classes or types of types. A distinction between what we call kinds, right? So which are types that classify things essentially, things that objects which are classified on that type are instances of that type in all possible situations. So it's related to this philosophical notion of essence. So here in this domain, we have people, brains, hearts, and organizations. So every person is necessarily a person in this domain, but people can be contingently a living person or a deceased person or a child or an adolescent or an adult. And likewise, an organization is necessarily an organization, but only contingently an active organization. So these are dynamic types, if you like, but there are dynamic types that classify things according to intrinsic property of these entities, right? So being a living person should be a person who has an intrinsic property of being alive. And we can contrast this with other dynamic types which are based on relational property. So no employee is necessarily an employee. Every employee is a person. But in order for you to move in or out of the extension of this employee type, you need to establish or terminate a relation to something else, right? So an employee is an adult person that has an employer, that has an employment that connects it to one or more employers. So we have here a distinction between kinds, between phases, and between roles, relationally dynamic types. And we have types which aggregate properties which are common to things of different kinds, like physical object. Every physical object is necessarily a physical object, but the type physical object itself does not offer a uniform principle of identity for all its instances, which can be people, organizations, organs, cars, buildings, and so on. These distinctions between essence and accidents, if you like, can also be applied to things which are not objects, but which are existentially dependent on objects, like the employment itself, or like the marriage. The marriage between John and Mary can only exist if John and Mary exist. The marriage between John and Mary is necessarily a marriage, but it's only contingently a happily marriage, or only contingently a marriage with full separation of assets, and only contingently a marriage that is legally accepted in Italy. Right? So being legally accepted in Italy is a role played by the marriage. What is legally accepted is the marriage, not John and Mary. We also have distinctions. All these distinctions I'm talking about are modal distinctions, right? There are distinctions which apply to things in different possible worlds. We have distinctions here that also apply to relations and which are modal. So the language makes a distinction between the relation I have with my brain and the relation I have with my heart, which are collapsed in UML and in many conceptual modeling languages. So for example, the relation between a person and the heart is a type-level dependence relation. Every person must have a heart, but the heart can change from one situation to the other, while every person must have that particular brain. It's not a type-level dependence, but an instance-level dependence, right? And this is just an example, right? We can think about a different domain in which every car must have an engine, but every car must have that chassis, because the identity of the car is connected to that particular chassis number. So if I can offer a geometrical metaphor, it's a bit like this. Our universe is a tessellation of kinds. Everything in the universe is of a kind, only that kind, and it cannot change that kind. Rows and phases are like shadows that move, classify, and declassifying things in the partition of one particular kind. And mixins, like physical objects, are types that cross the boundaries of multiple kinds. They can be rigid mixins that classify things necessarily, or dynamic mixins, which are shadows that move across the boundaries of multiple kinds. So just to give you an example on this tiny taxonomy of different types of types, making a distinction here between types which are either a kind or a specialization of a kind, which we call sortals. We have rigid sortals kinds, or dynamic anti-rigid sortals, which are phase and rows, and we have things which cross the boundaries of multiple kinds, which are mixins. Only by having this, we have a ontologically well-founded and cognitively transparent system of types, formally characterized system of types, right? So we can use this to actually classify things in reality by essential and accidental properties. Like, for example, this individual is necessarily a person, but he's only contingently an adult man, a senior citizen, and he's the same, he has an identity relation with this other individual, which is only contingently a boy, right? Mick Jagger is also contingently an actor and a singer, and there are counterfactual worlds in which he didn't drop out of the London School of Economics and he became an economist. So we want to do these operations that the same individual, Mick Jagger, is necessarily of this kind, but he can move in and out of these different extensions in different possible worlds. And we know that although all these things are different types that apply to Mick Jagger, they apply in different ways. They apply with different forces. Being a person is different from being a singer or being an economist. And this intuition has been there for a long time in the conceptual modeling and object-oriented modeling literature. But this system actually gives you a very precise way, a system of modeling guidelines that can tell you, given a general term in your universe of discourse, how you should model this. So for example, we have a very precise way to defend and describe why person should be a kind, a natural kind, and why singer should be a role. Singer is a role, or economist or British citizen is a role, because it's dynamic and it's relationally dependent. You can only be a British citizen if there is Britain, right? While a living person is a kind of phase because it's dynamic and it has to do with intrinsic property of the objects. It's a change in an intrinsic property that promotes a change of being an instance of that class. And we can even say that Mick Jagger is a cultural heritage item, like the Big Band is a cultural heritage item, and Mick Jagger is a kind of physical entity that has a spatial extension, or he's an insurable item, like this universe is an insurable item, right? So we have a system of types that are expressive enough to make honor to these different ontological and cognitive distinctions, and we have a number of methodological guidelines that help us to converge in modeling things in the same way, provided that we have the same worldview. But also, all these distinctions embed a certain micro-theory if you think about it. So the definition of what a role is in OntOUML is a theory about roles. It says, for example, that all instances of a given role are of the same kind. All instances of a role instantiate that type only contingently. Instance of a kind instantiate that role when participating in a certain relational context. So these are all constraints, right? But also, there are some constraints which are not obvious. For example, that a role cannot be a supertype of a rigid type. So I cannot do something like this. I cannot say that customer is a supertype of person, and you would think that no one would do that, but people do this all the time. People want to say things like that customers can be people or organizations, right? I took this from a UML book, and I can prove to you in few slides that this leads to a logical contradiction. Here it goes. Person is a specialization of customer. So by the semantics of subtyping, every instance of person is an instance of customer. So X is an instance of person in world W, which means that it's an instance of customer in world W. But because customer is anti-rigid, so it's dynamic, it means that there is a counterfactual world, W prime, in which X is not an instance of customer. Every customer can cease to be a customer, right? But now, because person is rigid, it means that in all worlds, that X exists, it is a person. So it means that even in W prime, X is a person, which means that in W prime, X is and isn't a person, which is a logical contradiction. This will happen every time we take a dynamic anti-rigid type and put it as a supertype of a rigid type. So now, because we have these constraints which form this theory, we can actually write synthetic constraints in the meta model of this language that would forbid the construction of models like this. We cannot have free floating roles. We cannot have roles as supertype of kinds. We cannot have roles defining a relation such that the Carnell constraint of this relation, capturing this relational condition, is optional, right? And we can embed this in a tool such that these ontological constraints become syntactical constraints, and the models won't compile, if you like. But it's actually more interesting than that. Because we can put this in a different way. Because of these constraints, rows can only appear in an OntOUML model following a certain structure connected to a cluster of concepts, following a pattern. So every time you have a role, it will specialize eventually a unique kind. It will be defined in a relation such that the opposite association end of that relation has a minimum cardinality constraint of at least one, right? Same thing for phases. So if we have a phase, it's eventually specialized a unique kind, and it has to appear in a phase partition with other phases, because everything which is in phase X will cease to be in phase X, but maintain this instantiation to a kind A, so it has to be in another, when it ceases to be in phase X, it has to go to another phase of the same kind. So again, we have a pattern. And there are other patterns which are a bit more complex. So for example, the case that I just mentioned, I want to model that the role customer can be played by people or organizations. As I said, we cannot do this because we run into a logical contradiction. So if we cannot put person and organization as subtype of customers, can I put person and organization as supertype of customer? Would that be possible? Would that be an alternative? Of course not, right? Because all kinds are disjoint. It means that customer is an empty class. So this model is saying that every customer is both a person and an organization, right? This problem is solved when we realize that customer is not a sort, or is not something which is contained in one single kind. That's exactly the problem. It's a mixin that crosses the boundaries, classifies things of multiple kinds. So we can take this and create a partition such that every specialization of this type is now something that only classifies things of a unique kind. That is a sortal. So we can take customer and specialize in personal customer and corporate customer, and the problem is solved. And we can do this for any mixin, regardless of the number of things which can play that role, right? And this is again a pattern, right? So the whole language is actually a system of patterns. It's a pattern language. Building models in OntOUML. So the modeling primitives are not these low granularity primitives like class, relations, attributes, and so on, but are these patterns. And you build models by putting together these patterns. And again, you can build a tool that does that. So we can go there. Oh, something got stuck. I had a video here. Okay, so I'll just reinitiate here. Let's hope the video, okay. So you go there and say person, and you write deceased person. It's a phase. Because it's a phase, there must be at least another phase, which living person, phase of the same kind. And then you instantiate this pattern. And you go there, and you say that I have a kind organization, and I have this active organization as a phase of organization, and the tool is sensitive to the semantics and knows that if active organization is a phase of organization, there must be at least another phase, which is extinct organization. And then again, I have another instantiation of the same pattern. And then a more complex pattern, which has to do with this role mixing I just mentioned. So I write there that personal customer is a role played by living people. That corporate customer is a role played by active organizations. That the role mixing in this case is customer. That the relational condition or relational context is a service contract. And the role in the other side, supplier, is played again by active organizations. And then again, voila, I have an entire model which is constructed basically by instantiating 3 patterns. And this is not, it's a non-trivial model. I actually can empirically show that most people would get this model wrong. Once I have this, I can now map this model from OntOUML to different implementation languages, including the semantic web languages, right? Through a relational database, to different object-oriented languages, and for example, to OWL, which is this language used in the context of semantic web. So I can go there and just generate this OWL code, including all the formal constraints which are behind that representation, which will be automatically generated. And then I can use any sort of, for the case of OWLs, any sort of reasoning tool or editor just to deal with my model as any OWL model. So I have now a kind of operational semantics to do reasoning with this model. Another thing I can do, and I think this is actually very exciting, and has to do with the essence of this problem of semantic interoperability is validation, right? So everything I showed so far has to do with verification, with checking consistency and satisfiability of the model and so on. As you know, verification is checking if you got the model right. Validation is checking if you got the right model. It's checking if the model represents what it was supposed to represent. And I would describe this validation problem by looking at the relation between 2 sets, right? So any model defines the limits, a set of possible instances of that model. It's represented here by the set A, the set of valid instance of that model, possible instance of the model, right? The set B is the set of intended instance. So the set of instance of the model that represent intended, desirable state of affairs in reality, according to the conceptualization. In the ideal world, these 2 things would coincide. However, frequently they don't, either due to a problem of under-constraining. That is, your model accepts instances which are valid but not intended, or the problem of over-constraining. So your model excludes instances which are intended, and they are not valid, but they should be, right? And this is obviously a major problem for semantic interoperability, because if you have 2 models, their valid instance can coincide without their intended instance coincided. So this is a problem known as the false agreement right? It's not a problem if we disagree, but it's a problem if we falsely believe that we agree. So things which are there in the intersection, but they are not there in the intersection between the intended instances or of these two conceptualizations or these two different worldviews. So what we want to do is to take a model that has those constraints that guarantees that these two things actually coincide, right? So that's exactly the problem of conceptual modeling. It's finding out what are the actual constraints that I should put in that theory about the real world, such that the instances of that theory, right, the possible interpretations of that theory coincide with the intended interpretations. The conceptual model is some structure plus some extra axiomatization, and this is the specification of your ontological commitment. So I strongly defend the view, if you want to use conceptual models or domain ontologies for semantic interoperability, these models have to serve as contracts. So they are not doodling mechanisms, right? They are really contracts telling the world what is your worldview. Telling the world what is the worldview which are represented in that model and hence in the information systems based on it, right? Every information system makes an ontological commitment. If it's explicit or not, it's another story. But everything which has some real-world semantics is a contract that captures a given worldview. And we want to guarantee that this ontological commitment is the intended one. These constraints, which are included in the model in OntOUML, some of these constraints are guaranteed by these patterns. So every time I use this pattern, I have a mechanism of theory inclusion. It will include a number of constraints that will guarantee that some of the non-intended models are automatically excluded, right? However, the language cannot do the same thing. So we can do that. As I said in the beginning, OntOUML guarantees that the only syntactically, grammatically correct models which can be built in the language are models that conform to the UFO axiomatization. But this is actually only true for the domain-independent constraints, right? Because a domain-independent system of representation cannot know about domain-specific constraints, right? It's the same with natural language. That's why we can say colorless green ideas leap furiously, right? So there is no way a domain-independent system can know about domain-dependent constraints. So how do we find out which are the domain-specific axioms that should be included there? And the way we tackle this problem is using simulation, right? A particular type of simulation. So what we do is that we transform this OntOUML model, so we have an operation semantics of OntOUML in a logical language called Alloy. And Alloy is a logical language which basically treats this as a constraint satisfaction problem and generates all possible instances of that model in a given finite bounded context. So if you take the model as a logical theory, the conceptual model, the conceptual specification as a logical theory, Alloy would generate all the logical models of that theory in a given bounded context. And the idea is that by showing this in a visual way to the user now can contrast what the model is saying on her behalf, and if the model is saying exactly what she wanted the model to say, right? So for example, take this model. It's a very, very simple toy model of a transplant, right? Here I have one kind, person, 3 rows, the organ donor, the organ donee, and the transplant surgeon. And these are roles played by people in the context, in the relational context of a transplant. Right? This model is syntactically perfect. It's not breaking any of those general ontological rules. But then now, I can simulate this model. So I can start generating visual representations of all possible instances of this model, again, in a finite context. So for example, I look at this, and I realize that, you know, I can have transplants with 3 surgeons, 1 donor and 1 donee, which is fine. And this is actually quite interesting from a pedagogical point of view. What we notice in practice is that people only understand the semantics of the model by looking at the instance, right? But as I iterate through the set of possible instances, this one will pop up. So this is a case in which I donate an organ to myself and perform the transplant. So I'm playing the three roles in the same relational context. And of course, I can have all variations of this. So for example, I can have an instance in which the donor and the surgeon are the same person, or the donee and the donor are the same person, but the transplant is performed by someone else, and so on. So when I test this to students, they all have the same initial reaction. They say, oh, I don't want the model to say this. Right? And my answer is, okay, so write something else. Write a different contract. Include a different constraint. And the first constraint they write to respond to this, it should declare the three roles as disjoint. Right? But of course, doing that is over-constraining the specification, because when you simulate this again, you find out that someone who donates an organ never receives an organ, right? Or a surgeon can never donate or receive an organ. So you're over-constraining, saying that these three roles are disjoint. What you want to say is that the three roles are disjoint in the scope of the same transplant. Right? So the idea is that you play the simulation game until you realize you adjust the axiomatization of the model such that you're neither over or under constraining this. This is actually quite interesting. This changed the way people do conceptual modeling, because now, since you have an operational semantics, it really approximates the way you learn conceptual modeling to the way you learn programming, right? People can go to this repository of these OntOUML models, download models, and start playing with the model. People learn programming by downloading other people's code and start messing with the code, changing things and executing, such that you understand, you have this immediate feedback of what that change promotes, and hence of what is the semantics of that. It's the same thing here. People download these models and start changing things, changing these stereotypes, changing stereotypes of relation, and simulate again. And they have a very, very fine understanding of the underlying semantics of the language by doing that. This set of tools connected to the language gave the language a certain popularity, so a lot of people started using it. So one example, one very interesting example is this department of the DoD, the US Department of Defense. They have been using the language, I think, for more than 10 years now. And this is an engineering department, it's not a research department, and they produce a really large number of models. And they have this booklet which is available on the web. And it's interesting, in the book, they actually highlight that the fact that the language was so useful to them was because it's computationally independent, so it's neutral with respect to technological choice, but quite precise. And what makes a difference there are really these ontological distinctions. Because of the, this kind of good publicity brought also by this group, this work, a lot of people started using the language in different contexts, and this allowed us to build actually a benchmark, a repository of OntOUML models in different domains, like ranging from biodiversity to electrophysiology of the heart, to public models about the public bureaucracy, government organization structures, for example, normative acts and so on. So these models here vary in domain, in size, so there are models which are pretty small that we took from articles or from theses, but also there are models which were built by a large number of practitioners over years, so over 2 years, and which are really large. So it varies on domain, varies on the type of people that were involved in building the models, the size of the teams, and the size of the models, right? So some of the models have 4,000 concepts, for example. And this allowed us to do the simulation across this repository. And when we start doing that, to actually check this, if there will be some systematic dissociation between the set of intended instance and the set of valid instance, patterns started to pop up. So actually, anti-patterns, so model structures that when present in the models would typically create this dissociation between valid and intended instance of the model. So the example of the transplant is actually an instantiation of this anti-pattern. Every time you have a relational context connecting roles that are played by things of the same kind, of course, more than one role can be played by the same entity. And we empirically found out that this is typically undesirable, unintended. Another example is this one. When we have two types and a relation between these two types, and we have specializations of these two types, indirect or direct specializations, you can have 50 levels of specialization there. But in the end, if you have a relation between specializations of these two types, typically we have a missing constraint between those two relations. So one example is this. I have a heart. Every heart is composed of ventricles, but when the heart plays the role of a blood pump, it needs the ventricle to play the role of a blood pump. An instance of this model that is hard, and we can empirically show it's hard for people to realize, is this one. So I have a heart, my heart has a ventricle, you have a heart and your heart has a ventricle, but when my heart pumps blood, it pumps blood with your ventricle and vice versa. So that's a possible instance of that model that most people won't realize. So by doing this, we actually made a catalog of anti-patterns, large number of anti-patterns now, and we start actually doing some empirical work by looking at this repository of models to actually quantify the occurrence of these anti-patterns. So here I just have these 6 anti-patterns, and for example, the one on relation specializations, we saw that it occurred in almost 50% of the models in the repository in 817 instances, right? Another one called the association cycle, it occurred in 92% of the models in 1,800 instances. Think about this. I mean, every occurrence of an anti-pattern like this is basically a situation in which the model says something on your behalf that you might not intend. And think about how this correlates to the semantic interoperability problem that I mentioned before. Here, the one on the transplant, this rollover pattern, it occurred in 1/4 of the models with 149 instances. These are impressive numbers. Right? So what we did after that was, so we realized that once we know these patterns, what we can do is actually, we can take a proactive strategy. So we can build in the OntOUML tool a way to proactively detect the presence of these patterns and tell the modeler that, look, if you include this part, you are actually accepting this and this and this as possible instances. Is there one that you would like to exclude? And once the modeler marks which undesirable instance to exclude, the tool will automatically include some systematically include some formal constraints to exclude those unintended instances. So we actually did a second empirical study in which we took the biggest model and the model that was built by practitioners. This was built by people in the Brazilian ministry, this was a Brazilian agency that regulates land transportation, right? And this was a model with nearly 4,000 concepts, a lot of relations, and built by a team of a dozen people across 2 years. So we gave them the tool such that they could validate this model, and we could record the number of occurrence of these anti-patterns that, according to these people, actually introduce a mistake, an error, right? And how often they would accept our predefined solutions, so our refactoring plans, rectification plans. And these are the results. So in the case of this relation specialization anti-pattern, in 88.6% of the case, this would introduce an error. And we could systematically correct this in 97% of the cases. So these are, in 97% of the cases, the modelers would accept our suggestion as a solution, right? And it varies in different patterns, but still, for example, for the rollover, it would introduce an error in 56% of the cases, and we could basically automatically correct it in 77% of the cases, right? Systematically corrected. We have some input from the user by marking some options, but then we automatically include the constraints, the formal constraints. So we were very happy with the results of this study, and then we thought about the next step, right? So we thought, you know, what if we go big? We are looking at models with 5,000 concepts, 4,000 concepts. So why don't we search for these anti-patterns in something massive like a weak data? So we select so this is the structure, the modeling data structure, if you like, behind Wikipedia. And what we did was to select 4 different anti-patterns which have to do with what is called multi-level modeling. So multi-level modeling is when you have a type that also behaves as an instance, right? A kind of power type phenomenon, if you like. So for example, here in this case we have creator is a profession, scientist is a creator, computer science is a scientist, and computer science appears both as a specialization of profession but also as an instance of profession, right? So it's an instance of profession. If you look at professions, computer science is an example of profession, but it's a specialization of profession. So there you have something like this, that Tim Berners-Lee is a computer scientist, and then you infer that Tim Berners-Lee is a profession. So when checking these anti-patterns on Wikidata, we have 17,000 cases of taxonomic structures that cross more than one level, that takes types also as instance, and in 15,000 cases they were wrong. So people would get this wrong in 85% of the cases, and these are cases which we can easily correct in a systematic way. So as a final example, if we look at this model, this is a very simple OntOUML model. It's a toy example of an ontology of criminal investigation, right? So we have one kind here, person. We have criminal investigation, which is one of these relational contexts, and different roles played by people in the criminal investigation: detective, suspect, witness, lead detective as a subtype of detective, and so on. And we have that the criminal investigation is composed of interrogation episodes, if you like. So this is, again, a model that is syntactically correct. There are no mistakes in this model. There are no roles which are supertype of kinds. There are no roles with missing cardinality constraints. There are no free-floating roles, and so on. This is a model that is syntactically perfect, right? But if we simulate this model, we're going to realize there are many possible instances here which are not intended instances. So would you guess how many anti-pattern occurrences do I have in a tiny model like this? So one obvious one is the one we saw before. So we can have a criminal investigation in which someone investigates himself and interrogates himself as a witness. Right? So the 3 roles are played by the same person. But we have many others. So there are 13 anti-patterns in this tiny model. So as I said, the tool detects all this. So we can, for one particular anti-patterns, run a simulation. So this is a simulation showing why this might be an instance that is unintended. So this is an example of the anti-pattern that I mentioned called association cycle. So this is someone, a detective, conducting an interrogation in an investigation of which he's not part. Right? So it's an example of this association cycle that should be somehow closed, constrained, and it isn't because there are missing constraints. So we can see that, and then the tool offers me some possibilities to exclude this model. So this is an example of an instance of the anti-pattern I just mentioned, this rel over anti-pattern. So I want to exclude this case that someone is investigating himself and interrogating himself as a witness. There are many possible ways to exclude that. So maybe all these roles are really disjoint. Maybe all of these roles are disjoint in the scope of one relational context. So for example, I want to say that so detective and witness cannot be the same role, or detective and suspect cannot be the role played by the same person in the context of a criminal investigation. But there are also constraints that cross different relational contexts. So I want to say, for example, that if someone is a suspect in one criminal investigation, he cannot be a detective on another one. Right? So the tool will offer all these different rectification plans, and once you mark this, what do you want to do? The tool would automatically include temporal OCL or OCL constraints to exclude those unintended cases. This, when you start using Alloy to do this, I got fascinated by the power of this tool and this approach of visual simulation. So Alloy is this logical language, as I mentioned, proposed by the MIT professor Daniel Jackson, who's the son of Michael Jackson, the computer science, not the singer, of course. And in his book, which is a very interesting book, I found, the first time I read it many, many years ago, I found this quote, in which he says, "Few modelers, however, have had the experience of subjecting their models to continual automatic review. Building a model incrementally with an analyzer, simulating and checking as you go along is a very different experience from using pencil and paper alone." The first reaction tends to be amazement. Modeling is much more fun when you get instant visual feedback. That's true. And then he goes on and says, "Then the sense of humiliation sets in, as you discover that there is almost nothing you can do right." I thought this was an exaggeration, but after looking at this and after collecting these empirical results, I think he was right. I mean, even I've been doing conceptual modeling for 20 years maybe, and I myself cannot build a model of any domain which is sufficiently complex without introducing these validation errors. And this is because we are just, I think we are just not smart enough to actually understand the consequence of this contract we are writing, to actually think about all these possible instances across possible worlds, right? So it reminded me of Dijkstra and his Turing Award paper, The Humble Programmer, in which Dijkstra says that, you know, building computer software and computer programs is something of a massive intellectual challenge. And we should be humble and realize that we are not fully equipped for that, and we should build the most suitable complexity management tools we can, right? So this is paraphrasing Dijkstra. What I have chosen to stress in this talk is the following. We shall do a much better ontology or conceptual modeling job in the future, provided that we approach the task with a full appreciation of its tremendous complexity, provided we respect the intrinsic limitations of the human mind and approach the task as very humble ontologists or very humble conceptual modelers, right? And it's really impossible. We have to be humble in face of this massive problem of semantic interoperability, especially given the consequence that this can have, the social consequence. And we cannot do this without relying on these 2,400 years of accumulated knowledge on ontology. As a final note, there is this very interesting Portuguese comedian and humoristic writer called Ricardo Araújo Pereira. And he once wrote that when the wise man points his finger to the moon, the madman looks at the finger. In order to do ontology, and in order to solve the semantic interoperability problems, we need to be able to look at the moon, at the finger, at the wise man, at the madman, at the wise man looking at the moon, and at the madman looking at the finger. We need to be able to have the full picture, the unified view of this entire scene, seeing viewpoints that no one is seeing, but at the same time being able to maintain all these different viewpoints. Thank you.
Thank you very much. Question?
I normally don't ask questions, but thank you for a talk which was enthusiastic and you gave a particular perspective. But at the end, I do not see how OntOUML improves on UML. So in a way, I am not convinced. And I think that partial reason is that all examples you showed could be, in fact, modeled properly in UML. And you started with anti-pattern yourself in the example with customer who can be a person, an organization. This is a bad model in UML because a customer can be a person, but the person is not a kind of customer. Therefore, no UML modeler will have a model like that. And then you build your argumentation on this example and similar example. At the end, you just give something which is much more complicated than UML, okay? And we know that only simple modeling techniques have been somehow accepted and used. Whether we are talking data flow diagrams, entity relationship diagrams, UML, people use them because they are simple. And finally, a comment about ontology. Ontology is like Esperanto. It's great, but nobody's using it.
I disagree with you.
Thanks for the provoking question. I mean, these things get really boring if everyone agrees. I couldn't disagree more, and the fact that you're not convinced means that I completely failed in my message, right? So I can answer in many different ways. So first of all, so you can actually model all of that using a Turing machine, right? You don't need even UML. You can use first-order logics. And the reason why people shouldn't use first-order logics is because you can do everything in first-order logics, but because it's completely neutral, you can do everything, including the gigantic number of alternatives that you shouldn't do. So you can do everything in UML, but in order to get the same models in UML right, you need to have a lot of experience, right? It would take people 20 years of experience in order to get those structure rights, right? You can do that, but it requires a lot of experience and mistakes. So the whole point of taking a language which is more expressive and including this kind of patterns and this kind of micro-theories in the language is that, one, you shorten the learning curve, so you don't have to wait 20 years for people to get it right. You guarantee a certain uniformization on the axiomatization, and you guarantee reuse, right? So this is the first answer. Second one is most people would get that thing wrong, so I completely disagree, and I can show you that you were wrong because I have empirical data that model, most people, most students, and unless you have people with a lot of experience, they would get that model wrong. As I said, I took it from a UML book, right? And there are many examples. This problem of modeling roles that can be played by things of multiple kinds, this was discussed in the conceptual modeling literature for years and years and years, and people came with really exotic solutions, and this is actually a really simple solution. And the third part of my answer will be about simplicity. UML is not simple. Like first-order logic, it's not simple. It just gives you the illusion of simplicity because in order to get the model right, the model that would play this role as a contract, really telling the world what is your worldview, this is the result of the combination of modeler plus language. If the language gets too simple, the complexity doesn't go anywhere. The complexity, you are completely transferring the problem of modeling and making the modeling choices to the modeler. The modeler has to have a lot of experience now to get that thing right. So what we're doing is taking known, correct modeling patterns and taking known anti-patterns and building this into the language such that the system, language plus user, can accept even users which are novice and they would get converging the same results provided they have the same conceptualization. And fourth, the OntOUML is very different from UML, not only in the sense that make all this explicit, but because it makes explicit this kind of model semantics, it allows for the seamless transformation to different implementation environments. So it's really computationally independent in this sense, and you can have very, very well understood patterns on how to model this to description logics, to relation database, to programming languages, and so on. Without this formal model semantics, we couldn't have had this approach of simulation in the way we did, and we couldn't have had the approach of anti-pattern detection. And also, from a cognitive point of view, again, the patterns emerge because you have this kind of model ontological semantics, right? And then, as I said, building the models become building, connecting all these patterns together, and understanding the models become by looking for these patterns, as opposed to looking at classes and relationships in separate. And as a final comment, ontologies are used everywhere. I can give you another lecture of real examples of ontology being used in a number of cases. Basically, you cannot do, I mean, all these different companies and these different tools that we use daily are somehow using ontologies.
Thank you very much.
Thank you again.